Okay, this video is about free fall objects falling under the influence of gravity only. Okay. No air resistance. Which means it has a constant acceleration because there is a constant force. That acceleration is equal to g. We give it its own letter because it is constant, and all acceleration is a vector quantity, has direction. This equals 981 centimeters per second squared, or 9.81 meters per second squared. Remember, that means 981 centimeters per second, or 9.81 meters per second. That means each second an object changes its velocity by 9.81 meters per second. In the downward direction. So it's important to remember that these are vector quantities and the direction is down, right? So down changes its direction in the downward direction, changes its velocity downward in the negative direction. So we're going to take a look at three different scenarios, right? An object dropped, an object thrown up, and an object thrown down. So objects dropped. Okay, if an object is dropped from rest, then we would say the initial velocity is 0 at the beginning, meters per second, but its acceleration is equal to negative 9.8 meters per second squared in the downward direction, right? So for all of these scenarios, we're going to take down to be negative, up to be positive. 1 second later, right, its velocity is going to be negative. So remember, this has direction to go with it as well. 9.8 meters per second. Its acceleration is still equal to negative 9.8 meters per second squared. 2 seconds later, so this is time equals 0, time is equal to 1 second. 2 seconds later, of course, it will have traveled a greater distance. Its velocity will be 9.81 plus 9.81, or 19.62 meters per second, negative direction, with an acceleration equal to negative 9.8 meters per second squared. At t is equal to 3 seconds, right? Time is equal to 3 seconds. An object will have traveled much further because it's going much faster. Velocity, we're going to add the 9.8 to that. So our velocity is still going to be negative, going down in that direction. So it'll be, right, adding the 9.8 on, 9.81, we'll have a 3, 14, 29.43 meters per second with an acceleration equal to negative 19.8 meters per second squared. So that's the case of an object that is thrown or just dropped, right? So it's just going to be dropped from rest, going down. It's going to go down, getting faster and faster, traveling a greater distance each second. But notice that acceleration is constant, right? No matter where it is, that's the same acceleration. What happens if I throw an object up, right? So another scenario, well, let's throw an object down. Thrown down, right? And we'll make the numbers easy. Again, taking down to be negative and up to be positive. At time equals 0 seconds, let's give it an initial velocity, right? At that time equal to, so we don't have to write the initial there. That's important in the equation, 10 meters per second. We'll just add that to our equation. And acceleration is still negative 9.8 meters per second squared in the downward direction. So 1 second later, of course, the object will have traveled a little bit further, right, than over in this scenario. So maybe it's right here, but it's still going to increase its speed by 9.81. Sorry, I have to throw on that extra 1. Okay, so the next second, it's simply going to be 9.81 plus 10, or 19.81 meters per second. But the acceleration due to gravity, because the Earth doesn't know what it's doing, is also still 9.8 meters per second squared. 2 seconds later, it's going to have traveled further, right? Because it's going much faster. Adding the 9.8 there, you're going to simply get 29.62 meters per second, with the acceleration equal to negative 9.8 meters per second squared. Of course, 3 seconds later, very fast, so maybe it's all the way here. So time is equal to 3 seconds, and it is its speed, in that case, velocity, given a direction. Its velocity, we're going to add just 9.81 to that, and you'll get negative 39.43 meters per second equals, and then your acceleration still being negative 9.8 meters per second squared. Right? So all that happens here is we add that initial velocity, and that falls true because the equation for what velocity do I have in any place in time is equal to the initial velocity plus acceleration times time, right? And since our initial velocity is negative, so is acceleration. You're simply adding your initial velocity, taking that acceleration times time, and that gets you your velocity at each one of these points. So mathematically, it should make sense. Physically, we're thinking about it making sense, right? Again, gravity, though, is constant. Well, the acceleration due to gravity is constant. The Earth doesn't know that I threw a ball down as to just dropping it. Our third scenario, then, is what happens when something is thrown upwards, right? So what happens when we throw something up into the air? Right? Object thrown upwards. Right? So for that scenario, we're going to have to start over here. So what I would like to do is let's throw it up. I need some more space. Let's throw it up with a velocity, my initial velocity equaling positive 29.43 meters per second. At time is equal to 0 seconds. My acceleration is still going to be negative 9.81 meters per second squared. For this scenario, we're still keeping down to be negative and up to be positive. So in this case, when you throw an object upwards, you have a negative acceleration, but a positive velocity. So the scenario here is, since acceleration is in the opposite direction of motion, it slows it down. It will slow the object down. So acceleration will have the effect of slowing it down. Okay. So our next scenario, right? It's going to be going pretty fast, right? So we can say maybe we are about right here. And our velocity in this case is going to be still positive, but it's going to decrease by the 29.43 and actually be the same value that we had over here when we were falling down at 19.62, right? So in this case, it's going to be going up 29.43 minus 9.8, 19.62 meters per second will be my velocity at t is equal to 1 second, if I threw it with this initial velocity. Okay, I'm using these numbers to make my scenario very easy. My acceleration is equal to negative 9.81 meters per second squared. Going up into the next second, right, it's going to be slowing down. So now I arrive right here, and my velocity is equal to the 19.62, right, minus the 9.81, gives me 9.81 meters per second is my velocity, positive. So what's happening on the way up is it's slowing down, right? The distance between each point, each second, is that it travels a less distance, right? Doesn't travel as far. So 2 seconds later, though, the acceleration is still negative 9.81 meters per second squared. Again, my change in velocity throughout this is always negative 9.8 meters per second for every second that I'm moving. So now I must go up and reach a point where I stop. So in this case, since I started with exactly the right number I needed to, in order that I would stop at exactly 3 seconds with a velocity equal to 0 meters per second, right? So an object thrown up is going to go up and up and up and up until it stops, right? So at that point where it stops, it must stop and then, of course, turn around. When it turns around, you're going to have the same scenario as the beginning, and it's simply going to fall back down with the same acceleration, which means it will equally have the same velocities, the same height on the way down. So at time is equal to 3 seconds, we could say that this object comes to rest. Acceleration is equal to negative 9.8 meters per second squared again, right? So it's going to turn around and fall back down. So an object thrown upwards travels up and up and up until it reaches a velocity of 0. So it moves up until velocity equals 0. The velocity going upwards. Upwards equals 0. Okay. All right, let's take a look at these scenarios again all together. Maybe pretty small. If we take a look at them. Oh, way too small. we go. Okay, I can drop something from rest, means my velocity is 0, and it falls down, increasing its velocity by 9.8 meters per second every second. Even if I throw an object down, it's going to increase in its velocity by 9.81 meters per second every second. When I throw an object up, my acceleration is in the opposite direction, and therefore it's going to slow the object down on its way up to the point where it reaches 0. All objects will go up and up until their velocity equals 0, and then turn around and come back down and follow this same scenario over here. So that's the case of free fall, and that is with the absence of air resistance. So when you're solving problems in free fall, in free fall scenarios, right? You always know the acceleration. Sorry about this printing here. Is equal to g, right? Has direction. So we're always going to take that as 9.81 meters per second squared down. I am always going to take down to be negative and up to be positive. You can choose otherwise. If everything in your problem is going down, you can certainly keep that as a positive. But that's what you always know. You always know that the velocity at the top equals 0 for an object thrown up. Okay, the velocity at the top equals 0 for an object thrown upwards. The velocity throughout the path throughout the trajectory is the same at equal heights above the ground. So what I mean by that is, let's say we are right here in this position, and this object is going to go up. It's going to go up and up, right? It's going to be slowing down until it reaches a velocity of 0. This is the maximum height. So it's going to go up and up until it reaches a velocity of 0. It's going to turn around, and at the same equal heights, it has the same velocity, right? So over here, whatever your velocity is, in this case, on this side, let's say the velocity equals x. On this side, your velocity is going to equal negative x. So it's just going to be in the opposite direction, but have the same value, no matter where you are in the path. So this is your maximum height, and the velocity is equal to the same on each side, just going in opposite directions. So notice I didn't put my vector quantity here because it's really describing the speed and the direction for velocity, which is the opposite. One's going up and one's going down. And the final thing to think of when you're solving the problems, the amount of time then, because that velocity is the same, the amount of time that it took to go up. So that should be a total time equals z, right? And say that from one position to the height, maximum height, it takes the same amount of time to fall back down, right? So to get to that same position, if I come back down, so this total time to come back down is also z, right? So those two times are going to be the same, which means if you're told that it takes 10 seconds for an object to go up and come back down and get caught at the same place, that means it reached its maximum height at 5 seconds, half of that time. So those are some major points to keep in mind as you think about an object in free fall when you're solving the mathematical problems. You always know g. The velocity at the top when thrown upwards is 0. The velocity throughout the trajectory is the same at equal heights above the ground. And the total time to go up is equal to the total time to come back down. So this is for an object in free fall. All right, so can you apply this information in solving problems with an object moving in free fall? So again, you can label initial velocity, final velocity, time. Acceleration is always g, 9.8 meters per second squared. And of course, maybe you're given some distances. Always remember, it won't be written, but it reaches a velocity of 0 at the very top of the path.